supralaryngeal factors. So let's turn the lights. Want to do a dim? I think it's the third. How's that? Okay. So the first one is just a review. I know you've had this in other classes. You guys haven't taken psychoacoustics yet, right? But your larynx really is, and your control of your laryngeal function results in the changes that we perceive as pitch, loudness, and quality changes of the voice. So if I phonate at my comfortable pitch, I'm doing that right now, my comfortable loudness levels, I do that with the aid of a microphone, and then you can make a judgment about my voice quality. Do I produce a clear tone? Am I slightly hoarse? Am I breathy? So those three characteristics, pitch, loudness, and quality, are things that you as a listener perceive, and so we call them perceptual characteristics. But there are physical events that correspond to those perceptual events, and what we do at the level really of the respiratory system and the laryngeal system is we control how fast our vocal folds are vibrating. We say that's the frequency of that's the frequency of vocal fold vibration. And two, we control the way we abduct and adduct the vocal folds, and that helps to control vocal intensity. So they're actually physical correlates to the perceptual characteristics of pitch and loudness and voice quality, really. And we're going to talk a lot about these characteristics. We're going to be showing videos of singers because they just have so much more control over their voices, and so I can give you these, kind of extreme examples of what we can do with our voices. So today we're going to be talking about the physical events of how we control frequency, fundamental frequency, and vocal intensity with our speaking voices. And then keep in mind that will correspond to pitch corresponds evidently to frequency, or obviously to frequency changes, and loudness to vocal intensity changes. So keep in mind, quality is a perceptual characteristic of voice. If you say, gee, I just heard somebody speaking and she's got a really breathy sounding voice, or somebody who has a cold and gets laryngitis and her voice is a whisper, those are qualitative evaluations of how a person sounds. And the thing that's important about these qualitative evaluations as a speech pathologist is that those are the evaluations that you make every day, like 100 times a day, depending on how many clients you see. So what are we doing in this class? I'm teaching you, basically, we're starting to talk about voice quality. It'll come up a lot, but I'm teaching you the underlying physical characteristics. I'm teaching you about the anatomy of the larynx and how the respiratory system functions and how that will affect voice quality. So as a speech pathologist, you're going to be making, excuse me, that's a little frog in your throat. That's not a term a speech pathologist uses, but nevertheless. You make perceptual judgments, but then you say to yourself as a speech pathologist, what could be the underlying cause of that? What's either the anatomical or physiologic cause of that voice quality? In a nutshell, that's why it's so important for you as a speech pathologist to understand the underlying anatomy and physiology and how it corresponds to the way you sound, right? Because if you don't sound, if your voice or your breathing patterns or your articulation doesn't sound normal, what does that mean? It means that something's wrong with the underlying mechanism. And speech pathologists have to understand the underlying mechanism to decide what kind of treatment you're going to use with your patient. You don't just treat the voice symptom, right? There's no point in treating the voice symptom. You have to treat the underlying mechanism. And that's part of what this course is all about. Okay, and last, other than the human ear, which is a really good instrument, there's no physical instrument that I can bring into the classroom to show you how to measure pitch, loudness, and quality. Those factors are all based on a human listener. And now, we do have equipment that we can use to measure the spectral components or the acoustic components of the frequency of your voices and the intensity of your voice, right? I do have equipment to do that. And the emphasis of this course is on the physical characteristics of voice production and speech production in general. Okay, another kind of review. You should have had this in another class. And when I'm talking about your fundamental frequency, and I've used that term a lot already in the class, what do I actually mean, all right? And what I mean is the lowest frequency or the lowest harmonic that you produce at the level of the larynx. There are other frequencies that your vocal folds produce. Remember, we talked about complex vibration of the vocal folds and that you don't just get a pure tone when you phonate. You get a complex vibration, which results in a complex tone. But for right now, let's talk about your lowest frequency component in your voice, which is called the fundamental frequency, sometimes the first harmonic, people refer to it. And basically what this part of the slide is telling you is that fundamental frequency is equal to 1 over time, or 1 over t. And it corresponds to the length of the period of one vocal fold vibration, right? So period is defined as the time taken to complete one cycle of vocal fold vibration. And we've looked at these cycles a lot, one cycle. We just looked at it at the last lecture. I showed you one cycle of vocal fold vibration. So the vocal folds will go from one cycle, if you think about it, but you could take it, one cycle could be defined anywhere on the waveform, as long as you take the point, you take the period of the cycle at the same point. But let's say we go from complete closure to maximum opening to complete closure. That was a slide that we looked at the other day. The vocal folds are completely closed, they open, they go to maximum lateral excursion, and then they close again. And that's what's referred to as the period. How long does that take? How long does one cycle of vibration take? A period, a typical fundamental frequency might be 125 hertz, right? And the way you would calculate that by this formula, if you know the fundamental frequency of a, well, let's say you don't know the fundamental frequency. I'm going to solve it for 1 over t. Let's say you know that it took 8 milliseconds for one cycle to complete, which is how fundamental frequency is calculated. So you go 1 over 8 milliseconds equals 0.125, and then you convert it to cycles per second or hertz, so you move it 3 decimal places, and that will equal a fundamental frequency of 125 hertz, right, or 125 cycles per second. That's more of a typical fundamental frequency for a male speaker, right, 125. Women, probably more around 200, 225, but I'm going to be going over those frequency characteristics. So when I say somebody's fundamental frequency is 125 hertz, I'm saying that that's 125 cycles per second. And then, if you can visualize this, maybe I'll draw this on the Wolf visualizer. If you can visualize that fundamental frequency is always inversely related to time, then you have to realize that as fundamental frequency increases, the time that it takes to complete one cycle decreases, right? So as frequency increases, t decreases, and vice versa. If frequency is decreasing or you have a low fundamental frequency, you have a larger or a longer time that it takes to complete one cycle. So you just visualize the cycle. Let's see what I have. Let me draw this. I'm going to put up one cycle of vibration. We'll talk about the period. I didn't bring any pen and paper. I just kind of walk over. Okay. This is my fault. I'm sorry. Internal PCs. Let's see what. Okay, we're. Do you guys know? As long as I'm drawing right now, there are flu shots over in the atrium and the biomedical building today and tomorrow for students and staff and faculty. The easy walk from here. Why was I thinking of that? Because I just got one. Okay. We look at a waveform. A waveform, by definition, is relative amplitude over time. So the waveforms that we've been looking at is relative amplitude as a function of time. All right? So let's say that I could record my voice. We do this a lot in our lab. And I just phonate, and let me do 2 phonations for you. This is going to be at my typical fundamental frequency. So I go, let's just say my fundamental frequency is about 200 hertz. Okay, and now I go, okay, I don't know what that was. 400. It wasn't that high. So I'm going to draw a waveform that corresponds to that lower fundamental frequency. Now the waveform, by definition, is, I'm actually have this acoustic signal. It's going to look something like this. Okay, and if I take my definition of a waveform from closure, let's say it's right here, closure to closure, that's how long it takes to complete one cycle of vibration. We've looked at a waveform like this before. And that's what's called T, or the period. Right? And that was that lower fundamental frequency. Now, if I look at my fundamental frequency, and I just said, let's say that this is, 200 hertz. All right, now I'm going to draw the waveform. This is a rough drawing, right? Again, it's relative amplitude as a function of time. And I'm just, I just excised 3 of those cycles out of my 15 seconds. And then I did that higher fundamental frequency, and the higher fundamental frequency is going to look like this. Right? So now if I go from closure to closure, and we measure the amount of time that takes, T, I'm not even going to put any numbers to this. This is a good conceptual drawing for you, which is, if I look at the lower fundamental frequency, I have a longer period. That's the inverse relationship right there. You have a lower fundamental frequency, but a longer period, or a higher period if you want to use comparable terms. Whereas if you produce a high fundamental frequency, then you have a shorter period, right? And so they're always inversely related. If your vocal folds vibrate many more times per second, if I go to 400 times per second, the period's got to be shorter, but the fundamental frequency is higher. Okay, so that's that basic relationship, and so you already know physiologically and anatomically how we control that. So, you know that you contract. I'm going to ask this question again. What muscle do you contract to control your fundamental frequency? Cricothyroid muscle, right? That's the one that rotates around the crico causes the two cartilages, the thyroid cartilage and the cricoid cartilage, to rotate. It places a stretch on the vocal folds, and when you stretch the vocal folds, they increase the fundamental frequency. So now the next slide says, why does the fundamental frequency increase when you place a stretch on the vocal folds? You stretch them, they get more tense. And it basically corresponds to kind of the mass, what we call the effective vibrating mass of the vocal folds. You know that even if you stretch the vocal folds, it's the same mass. You can't change the mass of the vocal folds, and that's why I qualify it with what we call the effective vibrating mass. So if we looked, let's say we looked at mass across speakers, absolute mass does have an effect on your fundamental frequency. That's why men have lower fundamental frequencies than women. They're taller, they weigh more, and their vocal folds are bigger. Well, everything, the respiratory system is bigger. So because they have more massive vocal folds, their fundamental frequency is lower. So mass makes a difference. But let's say that you're talking about if you could increase the effective vibrating mass of the vocal folds, if you could increase the mass of the vocal folds, then mass would cause a decrease in the fundamental frequency, right? And so if I compare mass across speakers, it's an easy concept, right? Bigger, more massive vocal folds would have a lower fundamental frequency. Now, but we also control our fundamental frequency. If I look at within speaker differences in fundamental frequency, you have to control the effective vibrating mass of your vocal folds, and you have to control the tension of your vocal folds. But basically, and we do this all the time, and basically the reason a larger mass of a vocal fold takes longer to vibrate is because it takes a longer time to start and stop the vibration. The vocal folds are moving. You got to get them started and you've got to stop them. There are what we refer to as inertial constraints on the vocal folds. It takes some work to accelerate the vocal folds, and it takes some work to decelerate the vocal folds. And the mass makes a difference. So if you have the general rule is a larger mass takes a longer time to start and stop versus the smaller mass, which takes a shorter time to start and stop. And so the smaller mass will result in a higher fundamental frequency. So how do we, here's that video again. How do we control the effective vibrating mass of the vocal folds? So let's review this video once more. After this lecture, we're moving on from this video.
You'll now see two examples of rising and falling scales sung by a countertenor. This is a thoroughly typical example of the male falsetto mechanism. The free edge of the folds is thin, vibration amplitude is moderate, and there is little mucosal wave. The closure phase is very short.
Top of the range and the bottom of the range. Okay, and well, that's it. So you see the definite stretch. Now let me point out from this video about the effective vibrating mass. You heard the talkovers say that notice that that the edges are thin and the edges are vibrating. If you only allow the edges of your vocal fold to vibrate, then you're changing the effective vibrating mass, right? The rest of the vocal folds are taken out of the vibration. And if you stretch them and place more tension on the vocal folds, what's going to happen? The recoil is going to be faster because you have a more, I don't want to say elastic. Let's just say a stiffer elastic object. Okay, and the stiffer elastic object will produce a faster recoil force. So you increase the recoil force by affecting the tension of the vocal folds. Okay. This is a question for you to work out for next time. Or you can do it just in your head this time. What's the fundamental frequency of someone with a period of 4 milliseconds? If it's 1 over t, it's basically 4 into 100, right? So you do the calculation and make the decimal move in your head. So what's this person's fundamental frequency? Yeah, 250 hertz, right? So, so you can see, again, the frequency is higher, but the period is lower than the previous example that I gave in class. Okay, so now let's talk about how we control, this is basically a within speaker description of how we control fundamental frequency, or how a person controls fundamental frequency. We've talked about the first mechanism quite a bit, which is contraction of the cricothyroid muscle, which is you lengthen the vocal folds. When you lengthen the vocal fold, you get a thinner, more tense vocal fold, and that results in the fundamental frequency increase, which would result, of course, in a perceived pitch increase. Okay, another mechanism that we use for controlling fundamental frequency is you can actually alter the tension within the 2 thyroarytenoid muscles. And what are the 2 that we're talking about? We're talking about the thyrovocalis and the thyromuscularis that make up the body of the vocal fold. So let's say that you can not change the length of the vocal fold, but you want to just change the tension of the vocal fold. Do you remember that isometric contraction that we talked about earlier in the course? And that is, you can actually tense a muscle without changing the length of it. So let's say you keep the length of the vocal folds the same, but the tension changes. That changes the elastic characteristic of the vocal folds, and they would, if you increase the tension, that would increase the recoil force, and so therefore they would recoil faster to midline. And they'd be displaced faster, too, by that subglottal pressure that you're controlling. So one way that we can additionally alter our fundamental frequency is by a tension within the 2 thyroarytenoid muscles. So in other words, that muscle is exerting a local tension change, even though there's not an overall length change. And we probably do this all the time. You might do it when you want to change your fundamental frequency within a register, or maybe when you change registers, and we'll be talking about registers in a little while. Now, the other mechanism, this actually question was on an ASHA exam once, which I was really surprised about because it's a pretty detailed question. Because what we do is, remember, we have full control over opening the vocal folds and closing the vocal folds, right? With our intrinsic laryngeal abductors and adductors. Well, if you remember what your adductors are, the interarytenoids and the lateral cricoarytenoid muscle. Well, let's say you use those 2 muscles simultaneously and you tightly adduct the arytenoid cartilages together, right? So you've got a very tight adduction. What have you just done? If you tightly adduct the arytenoid process, the arytenoid cartilages, and you're kind of tightly adducting those vocal processes, right? Because that's on the base of the arytenoid cartilage. If you tightly adduct those cartilages, which tightly adducts the vocal processes, you don't allow that part of the vocal fold to vibrate. You take out the back of the vocal fold in terms of vibration. They will not vibrate. And so you've shortened the vocal fold. So the way this is typically described is that the vocal folds at the posterior glottis are tightly compressed. You shorten the vocal folds. You've decreased the vibrating mass of the vocal folds, and that will have the effect of increasing the fundamental frequency. Okay, last, another mechanism, and this isn't the primary mechanism, but it is a mechanism that affects fundamental frequency, is if you increase your subglottal pressure, you will increase your fundamental frequency. And that follows from our lecture from last time and the aerodynamic forces that are acting on the vocal folds. What happens if you increase your subglottal pressure? How will that impact the frequency of vocal fold vibration? If you increase your pressure, it'll blow the vocal folds apart faster. And if you blow them apart faster, they're going to recoil faster to the midline. And that's really exactly what happens. So that increases in subglottal pressure will impact the frequency of vibration. This happens to all of us. Remember I gave you that example last time? You just involuntarily, if you want to know the truth, you involuntarily increase your fundamental frequency when you increase your vocal intensity. So if I go, and I'm just going to try to increase my fundamental frequency, and I go, I really increase my vocal intensity. To do that, I increase my subglottal pressure, and at the same time, my fundamental frequency probably went up about, not much, 15 maybe to 20 hertz. You don't get huge increases. But subglottal pressure can be an important mechanism for helping you increase your fundamental frequency. Okay, so these are for controlling fundamental frequency. These are the four major mechanisms for what we do when we either really think of the opposite when you want to lower your fundamental frequency, but we'll talk about that too. This is the mechanism we use for controlling fundamental frequency and increasing it. These are all increase mechanisms, but you would do the opposite to decrease it, right? So any questions about those four mechanisms? Okay. So now we'll move on to how we control our vocal intensity. And again, what do we have at our disposal? We have the respiratory system. We have what we do at the level of the larynx. And, I could actually add a fifth component, but we're not talking about supraglottal stuff. I'll add it when we get to it, what you do when you increase your vocal intensity. So first, actually, a primary mechanism that helps you increase your vocal intensity is you raise your subglottal pressure. So if you want to talk louder, a typical way of doing this is to raise or increase your subglottal pressure. You can do it in other ways. You don't have to increase your subglottal pressure, but most people do, and most people increase it by quite a bit. Okay, the second thing that we do, so subglottal pressure, let's think about subglottal pressure. What would it take? What would you have to do to increase your subglottal pressure? By now, that should be a straightforward. How would you increase your subglottal pressure? What? Well, yeah, you'd go to a higher lung volume. You could take advantage of the recoil forces that we talked about for that whole first part of the semester. Typical speakers do that. So many speakers will just naturally go to a higher lung volume, so they have higher recoil forces. The other thing you do is compress a little bit more with your expiratory muscles, right? So a combination of elastic recoil of the lung thorax unit by going to higher lung volumes and more forceful contraction of your expiratory muscles will just naturally increase your subglottal pressure, whether or not you're doing anything here, whether or not you're doing anything at the level of the larynx. But remember, at the last lecture, I said, gee, the larynx and the respiratory system are really, they're actually innervated by the same nerve, and they're actually feedback systems that control both the larynx and the respiratory system. It's the same feedback system. It's referred to as the vagal volume system. So at the same time, we are controlling what we're doing at the level of the respiratory system to control subglottal pressure. We're controlling the laryngeal valve, right? Which is right, you guys know by now, it's right at the top of your pulmonary system. You have a valve, that's controlling inhalations and exhalations. And if you alter the configuration of that valve, or in other words, if you alter the configuration of the glottis, you can help build subglottal pressure, right? And so what's going to help you build subglottal pressure? If you keep the vocal folds closed for a longer period of time, let's just say, during one glottal cycle, or not to mention, for your entire sentence, you want to talk louder. So what's going to help you talk louder? 1, respiratory support. 2, laryngeal function to basically increase the resistance at the level of the glottis. And we do that in really 3 different ways. Number 2, number 3, and number 4 are really very important mechanisms for controlling the valve at the level of the larynx, to either keep it more open or to close it faster, or to close it more, to keep it closed. So the first mechanism, and these are just, people thought up these measures, but they've been around for so long, it's just kind of referred to as a mechanism. But there's a real mechanism in controlling your vocal intensity. One is, don't even look at what's up there yet, but these are measures that we use to measure the mechanism. The mechanism is you keep your vocal folds closed for a longer period of time, and you close and open the vocal folds faster. They open faster, they close faster. But one of the real mechanisms is that you keep them closed for a longer period of time. And these measures help you measure that mechanism. So the first measure we look at to establish what's going on at the level of the larynx when you increase vocal intensity is referred to as open quotient, okay? And that is, by definition, the duration of time that the vocal folds are open versus the duration of the total cycle, over the duration of the total cycle. So it's a ratio. There's no hertz put on it. There's no decibels put on it. It's just a ratio of, it's a temporal. It reflects a temporal event. So the general relationship between these two is that, and this is important, as open quotient decreases, as that ratio gets smaller and smaller and smaller, vocal intensity increases. Okay, let's go to the Wolf visualizer again, because I want you guys to understand this visually. Okay, I'm going to draw another waveform, another 2 waveforms at the bottom. So again, this time, the phonation is going to be, I don't want to change my fundamental frequency. I might in the demo, but I don't want to change it on paper. So I go, ah, and I go, ah, almost kept it the same. So on the first one, I did a comfortable vocal intensity. And the waveform's going to look kind of like this top waveform that I put up. Okay, but I'm just going to show a couple different cycles. Again, this is just looking at relative amplitude as a function of time. We're looking at a waveform. And the vocal fold during a comfortable vocal intensity, am I on the paper? Yes. Will look something like this. Notice that the open time, the time it takes to open the vocal folds takes longer than the time it takes to close them. That's normal. closed for a period of time. So the cycle is always a little asymmetrical. Okay, now if I just do that same fundamental frequency, but I go to a higher vocal intensity. Let's draw this next part, this next waveform. It's going to look more like this. Okay, so if I measure the period from here to here, and the period from here to here, so they have the same frequency of vibration. But notice that, what can you see just by eyeballing the waveforms? When I go louder, are the vocal folds open for a longer period of time or closed for a longer period of time? They're closed for a longer period of time. You spend more time in the closed part of the cycle. So we're closed, here it's open, closing again, and closed. So the vocal folds are closed from here to here, and from here to here. That's more time in vocal fold closure. Versus in this waveform, the vocal folds are basically open right about here, and they stay open until there, right? Here, they're open just for that amount of time, and open for this amount of time. So the open time is much longer when it's a comfortable production, whereas the closed time is much longer in a high vocal intensity. So now let's go back to that. So now you have the visual picture of it. So we're controlling that laryngeal valve. We're keeping it closed longer. It does a couple of things. It helps you build up subglottal pressure. And two, it changes the acoustic characteristics of the waveform that you're producing right here, right? It changes the spectral components of the waveform. So let's go back to the formula for open quotient, which is the duration of time the vocal folds are open over the duration of the cycle. So the duration of the cycle, let's just say you put in a constant value in the denominator of this ratio. You know, it's just a division problem, right? And then the duration of the time the vocal folds are open, it gets smaller when you increase your vocal intensity. So the numerator is going to get smaller, which means the open quotient is going to get smaller. So in other words, open quotient will decrease as vocal intensity increases. It's straightforward. Yes. Yes. Open quotient gets smaller or lower as vocal intensity increases. Okay, now the other thing you can notice from that picture, can you visualize the picture? Or should I let me stick it back up for speed quotient. But first, let's look at just by definition, this is speed quotient. Now we're talking about the time it takes to open the vocal folds. You know, you measure the time, 2 milliseconds, over the time it takes to close the vocal folds, let's say 1 millisecond, right? So the speed quotient, it typically is above 1, but what you're looking at is the time it takes to open the vocal folds versus the time it takes to close them. And many times I'll just kind of abbreviate that as opening time over closing time, right? And if we look at this waveform, again, the same waveform that we looked at a minute ago, we look at that waveform, what we're really looking at when I say the time it takes to open the vocal folds, okay, here's maximum lateral excursion on low intensity. Here's maximum lateral excursion on high intensity. So what happens? It takes less, if I measure the time it takes to open the vocal folds here versus here, this is the time it takes to open them. So how long does it take in the high intensity? A shorter amount of time, right? But the other thing, because speed quotient is a ratio, this takes longer to close up here, but it takes shorter to close here. Usually in speed quotient, both the opening time and the closing time are changing. Sometimes they can change equal amounts, which means your speed quotient won't really change too much. If you change both the numerator and the denominator.
Can you repeat what you just said with the time for opening?
Yeah, look at what I'm pointing at. So what happens is the time it takes to open is this time right here, right? Or from here to here. Now in the lower one, the time it takes to open is from here to here, or in other words, right here. So you can see just by looking at this, it takes less time to open in high vocal intensity, and it takes less time to close in high versus normal. So they both get shorter. But because this waveform is always an asymmetrical waveform, speed quotient is always is always a positive number. Okay, now the last mechanism that we're talking about. So the speed of opening and the speed of closing changes. You want that valve closed, and so you close it faster. And it does the same thing that open quotient does. It helps you to build up the subglottal pressure, but it also changes the acoustic waveform at the level of the larynx. So right here, we've talked a lot about airflow and air pressure, and I've said to you before, it's all about the shape of this airflow waveform that's going through the glottis. But this is where that airflow energy gets converted to acoustic energy, right? This is where the vibration of the vocal folds becomes acoustic energy right here. So we can actually measure it acoustically and look at what, the vibration of the vocal folds has, what acoustic effect it has. So now let's go back to our list again. And the last one is also pretty straightforward to visualize from the two figures that I just drew, which is the last one is referred to, and this is, I think, a really important one. I like, well, number one, for sure, you've always got to think about. Number two, open quotient always changes when you change your vocal intensity. Speed quotient doesn't always change when you change vocal intensity because the speed of opening and closing changes. But maximum flow declination rate is another one that always changes with changes in vocal intensity, and that is called, by definition, the maximum flow declination. So in other words, when the airflow through the glottis is getting lower and lower and lower, it means that the vocal folds are closing. That's the only time it gets lower and lower and lower. So it's called airflow declination rate. It's a reflection of how fast the vocal folds are closing. And basically, the higher vocal intensity, the higher the maximum flow declination rate, or as it's abbreviated, the higher the MFDR. MFDR reflects the rate of vocal fold closure. And the faster the rate of vocal fold closure, the higher the MFDR, and the higher the vocal intensity. Yeah, the whole thing? Okay. So the maximum flow declination rate, as the flow is decreasing, so you're on the closing part of the cycle, is reflecting the speed of vocal fold closure. Okay? And basically, the faster the vocal folds close, the higher the MFDR, and the higher the vocal intensity. The speed quotient thing one more time? Okay, let's go to the waveform, because I think, will that be helpful? But just keep in mind, by definition, speed quotient is the time it takes to open the vocal folds, or vocal fold opening time, right? Versus the time it takes to close, or vocal fold closing time. Okay, now if we go to the figure, if I look at the time it takes to open the vocal fold, this was the comfortable vocal intensity. Let me just put comf right here. Okay, and here is high, right, this waveform. Okay, and this is the relative amplitude. So in the comfortable one, look at how, if I define, I have to know when the vocal folds are closed and when they're open. So I'm going to say right here is when the vocal folds open, and here's when they get to the maximum lateral excursion. So the time between here and here is this on the abscissa of the waveform, right? Is the time it takes to open the vocal folds. Now, the time it takes to close the vocal folds runs from maximum lateral excursion to when they close right here. So this is the time it takes to close the vocal folds, right there. And you always get this asymmetrical time. It always takes a little longer to open the vocal folds than it does to close them. Okay? Now, when you go to a high vocal intensity, what happens is now the time to open the vocal folds is very short. So it takes the time from here to here. That's a shorter time to open. And it's a shorter time to close because they close from this point to this point. The time it takes to close is also shorter. Which means that the reason that's, I think speed quotient, Deb and I have been talking about this because we're working on a study right now. I think speed quotient reflects an important mechanism. And the mechanism is you open your vocal folds faster and you close them faster. But because both of those times change when you increase your vocal intensity, you can't always get big changes in speed quotient because the ratio, the numerator might change the same amount as the denominator. So I like MFDR a little bit better because you always get a really fast closing time when you increase your vocal intensity. So if you just look at the closing time, and the other reason the closing time is important to look at is if you go to the acoustics literature on vocal intensity, I might have that on the next slide. The conversion from aerodynamic energy to acoustic energy, the way we control vocal intensity, happens, I don't know why, I don't know the physics of this, so I don't know why, but this is true, is that the conversion, let's go to this waveform again. A really important point in the cycle to make your voice louder tends to be right about here. Usually your fastest closing time is right about here. It's very close to the baseline. Or in other words, it's right before you close the vocal folds. You have a very narrow glottal opening, and if you have a fast time right in here, you tend to be able to convert it to a high vocal intensity. So the physics of this has to do with closing your vocal folds very fast, especially near closure time. So this part of the cycle, the closing part of the cycle, tends to be very important for the acoustics of the speech of your voice, the acoustics of your voice. And I will now go to this next slide. We're skipping this one. Everybody cross it out. We've already talked about it. And I don't wanna mix people up with this. It's a good slide, but this is the one I like. Was for MFDR you're talking about? That one is the faster, the higher the MFDR, the higher the vocal intensity. These are the mechanisms we're talking about for controlling vocal intensity. If I go back to this slide, look at the top, I've got these are the important mechanisms for controlling sound pressure level. You can write in vocal intensity. We can measure sound pressure level, but it's directly related to vocal intensity. And the higher the MFDR, the higher the vocal intensity. Okay, so now everybody's putting an X through this. I'm not going to ask any questions about this slide, but basically it's saying that there's a relationship between subglottal pressure and glottal resistance, and that those two are always interacting. Okay, now, when I've said to you the acoustic characteristics of voice, right, we're really talking about the frequency components of your vocal productions and just what's down here. I'm not even talking about how you alter that with the vocal tract. So right now, we're just talking about the sound source that you produce due to vocal fold vibration, right? And I don't know if anybody has said this to you yet, but if you could, in fact, cut off, your resonating cavities, which is your pharynx and your nasal cavities and your oral cavities, and you could listen to this sound that's produced at the level of the glottis. It kind of sounds like a buzzing sound. It's a buzzer type sound. That's what's powering, not powering. This is powering. This is converting to your sound source right here. Has anybody said it's like the raspberry sound that you can make with your lips? So if you do something like this, there's no above vocal tract. You go. That's the sound you're making at the level of the glottis. It's a very complex vibration. Not exactly. Word has it that there was, this is not a nice story, but there was somebody, again, at one of the university hospitals, and he had, because how can you get at that sound without the vocal tract being, without the whole resonating cavity system being there? You can't. But this guy had carcinoma of his mandible and tongue. And they did studies on him after his jaw and tongue were removed. And so they could actually do a microphone recording of the sound, all right? But people know this from the frequency components also. And what you do when your vocal folds are vibrating, you produce this complex periodic sound, which has a strong fundamental frequency that we've been talking about so far. Your lowest frequency component, which is also your first harmonic. But then, because it's complex, you produce a series of overtones or harmonics along with the fundamental frequency, all right? And so let's say, now, by definition, again, this is a spectral display of voice. And a spectral display, if somebody says you're looking at a spectral display, you're always looking at relative amplitude, right? Relative amplitude, so you're looking at the amplitude of those signals, or we could put decibels on here, sound pressure level in dB, we could put that on here, but now it's a function of frequency, not time. So you're not looking at a waveform anymore. You're looking at relative amplitude with the frequency components of the sound. And what's the amplitude of those frequency components? Well, this is a person who has a fundamental frequency of 200 hertz, right? And we have the acoustic analyzer to do this. And that person's fundamental frequency is 200 hertz. So if it's at 200 hertz, this is 100, 200, 300, 400, 500 hertz right there, and so on, okay? So each of these, the distance between these hatch marks is 100 hertz. So this is a 200 hertz fundamental frequency, and if you look at the length of the line, that's telling you about the relative amplitude of your fundamental frequency. So what do you notice about the relative amplitude of the fundamental frequency? Not only is it the lowest frequency component, it has the highest amplitude. It's also the highest amplitude component. Right? And then and this is also referred to as the first harmonic. And then what you produce as a human speaker, you produce these harmonics that are mathematically related to your fundamental frequency. They're consecutive integer multiples of the fundamental frequency, which means your first harmonic is going to be your fundamental frequency times 2. So your second harmonic is your fundamental frequency times 2. Your third harmonic is your fundamental frequency, whatever that value is, times 3. Your fourth harmonic is 200 times 4, and so on. Okay? So this is what a typical and what's, you can identify with as a normal voice source. And what you see is that the fundamental frequency at 200 hertz is your highest amplitude component. Your second harmonic is 200 times 2, which is 400, right there. Your third harmonic is 200 times 3, which is 600 right there. And your fourth one that we just said was 200 times 4, so it's at 800 hertz. Consecutive integer multiples of the fundamental frequency. What's the next thing you notice about those harmonics? What happens to the amplitude of the harmonics? They decrease. So you can see that easily from this spectral display of a voice source is the highest amplitude, or in other words, the loudest frequency component. It's really the highest intensity frequency component, is the fundamental. And then it goes down. And then the amplitude of this is the second, the amplitude of the third harmonic is even lower. Amplitude of the fourth, lower again. Amplitude of the fifth, at 1,000 is low. See, they go down, and there's actually a decibel relationship between those harmonics. But just what I want you to remember about the spectral display of a voice source, of the sound that you make at the level of the glottis, is that as frequency increases, as the frequency components increase in the voice source, the amplitude of those components decrease. Right? You can see it right from the picture. As frequency components increase, amplitude of those frequency components decrease. The little lines get shorter and shorter and shorter. And this is a normal voice source. Now, in order to determine your vocal intensity, you can see that the fundamental frequency makes a big contribution to your overall vocal intensity. Yes? It's F0. It's the fundamental frequency. It's the lowest, or sometimes the first. Sometimes people say F1, or the first harmonic, or H1 is the first harmonic.
So F0 is the first harmonic?
F0 is the first harmonic. What else? Yeah. You can change your fundamental frequency, yeah. If I go ah versus ah, I've changed my fundamental frequency. So if I go ah, let's say my fundamental frequency is 400 hertz, then what's my second harmonic? 400 times 2. So now my second harmonic is 800 hertz. My third harmonic is 400 times 3. Okay. If F0, if your fundamental frequency is 200, your second harmonic is 400. I don't want to call the other ones F2. We abbreviate fundamental frequency in our field as F sub 0. Okay? But then you refer to the other tones that you produce as harmonics. So then it's F0, or let me just say H1 would be harmonic number 1 versus harmonic number 2 versus harmonic number 3. That's typically how they're talking about it. Okay? What else? Anything over here? Okay. Yes?
Sorry, I'm still kind of confused. So that
Okay.
the first line is the
Fundamental frequency.
F0, first harmonic.
Yes.
So the one next to it would be the F1 value?
No, the next one to it is the H is the second harmonic, or H2.
Okay.
This is H2, second harmonic. It's 200 versus 400, and then this one would be H3.
But like in our phonetics class, we just refer to it as F1, F2, F3.
No, you're talking about formant frequencies,
Oh, okay.
right? She's talking about formant frequencies, and that's different than the sound source. So the sound source is the acoustic signal you're producing due to vocal fold vibration. Formant frequency 1, formant frequency 2, and formant frequency 3 have to do with the resonant characteristics of the vocal tract. So it has to, it's another acoustic, which is another way we control vocal intensity is the shape of the vocal tract up here, but I'm not talking about that now. But that is, those are actually change and alter the acoustic components of your voice. Yes?
So, just to clarify, F1, F2, F3, those are your formant structures because of the natural resonating frequency in your supra.
Yes.
And then the first harmonic, F0, that's your fundamental.
F0 is your fundamental.
And then harmonics, 1, 2, 3, that
has to do with your fundamental also. The harmonics have to do with your fundamental frequency. Whereas the formant frequencies are due to the resonant characteristics of the vocal tract.
So this is just having to do with the level of the
Your voice source, only with the sound that you're producing at the level of the larynx. And they all add up together to produce what you perceive as speech production. So whatever acoustic characteristics you're producing here are basically powering the rest of the vocal tract, and then you reshape the vocal tract or your resonant cavities to produce different formant frequencies. Okay, so let me give you an example of how these interact. So let's say I'm producing a fundamental frequency in harmonics at 200 hertz, and I go, and then I have a certain shape of my vocal tract up here, and my F1, F2, and F3 will correspond to the shape of this vocal tract. But if I go E, same fundamental frequency in harmonics, but I reshape my resonating cavity, F1, F2, and F3 will change, be very different from an E versus an Ah, and then if I go ooh, this is the same, but this changes. Okay? So that's how they interact. And the whole time, of course, you're controlling subglottal pressure to power the whole system. Because if you don't have air flowing through the system and certain air pressures that you're producing, you can't produce speech either. So all three systems work together to produce ah, e, e. Okay? Anything else? All right. So this spectral, if you can understand this one, then the next one I'm going to draw for you is going to be how does this spectral display that we have of normal voice change when we produce loud vocal or high vocal intensities and you perceive it as loud. Now, before I go on, I had just started to say, and this is important, that the overall intensity of the voice, and this is a conceptual formulation, the overall intensity of your voice is determined by basically adding the amplitude of all of these frequency components together, and your overall intensity is determined by the amplitude of all of those frequency components in your voice. So your fundamental frequency contributes a lot, and then these consecutive integer multiples at lower amplitudes all combine to give you your total vocal intensity. Okay? You know, you could add this one as, this one might be 10 or whatever, and this one might be 6, and so on. You just add them all together to get your vocal intensity, the amplitude of them. Now, on high SPL source, we're going to look at a slightly different, what do you do to increase your vocal intensity? You increase your subglottal pressure, right? You decrease your open quotient. You probably increase your speed quotient. Closing becomes a little faster, and you're going to increase your MFDR. What acoustic effect does that have? So now let's look at the new spectral display of your voicing signal. This is just a voicing now. We're not talking about formants at all. Here, I'll just draw on the back. I didn't think about drawing so much today. Okay, now I'm going to draw a spectrum of a voice source at a high vocal intensity. So by definition, when I say I'm going to look at a spectral display, I'm going to look at the frequency components of your voice as a function of their relative amplitude, right? And so we're going to do relative amplitude on the ordinate. Frequency components here, and this will be in hertz. All right, let's take the same voice source, which was 200 hertz. So let's say my fundamental frequency, which I would abbreviate as F. Usually you'll see F sub O. It's really F sub 0. And let's say that that is 200 hertz. Okay. Now I'm just going to draw in the harmonics. So what's my second harmonic? And this is also called H1. Right? So what's my second harmonic going to be? 400, right? Because it's 200 times 2. So H2, harmonic number 2, is going to be 400. And I'm going to draw this in. I'll just put these at the bottom first. So 400. And then my next harmonic is going to be 200 times 3. So my next harmonic will be 600. And then it'll be 200 times 4, so it'll be 800. And let's do one more. The fifth harmonic will be 200 times 5, so it would be 1,000 hertz. So my fundamental frequency is the same. It's 200 hertz and still going to be the highest amplitude frequency component of my voice. And if you phonate into a microphone and you have, all of you guys can download any kind of voice analysis program you want. There's all kinds of them out there. And you could each measure your fundamental frequency using this free software. And what it measures is your highest amplitude component, which is also going to be your lowest frequency component. So each of you could measure your fundamental frequency. It probably won't give you your harmonics. You need a more sophisticated program. It might to get your harmonics. But what's my harmonics? Now, in normal vocal intensity, the picture that I showed you before was the second harmonic is going to look something like this. The third harmonic like this. The fourth harmonic this. And the fifth harmonic something like that. Okay? So you have, if I draw a line and I connect the tops, so, we're looking at the amplitude of each of those harmonics. Where does it line up over here? What's the amplitude? The amplitude of that one and that one. If I draw a line connecting the tops of each of these amplitudes, it's referred to as a spectral envelope. Okay, so there's the spectral. You kind of look at the slope, and you look at the slope of the line, and you've got your spectral envelope. Now I'm going to go louder. Okay, my fundamental frequency is the same as 200 hertz, but the amplitude of the fundamental frequency is going to go up for loud, right? The amplitude of all of them is going to go up. And then when you add up those amplitudes, you've got a higher vocal intensity. But something a little special happens with high vocal intensity. Not only do they all go up, the ones in the higher frequencies, they go up. So 400 is going to be a little higher. As you get into the higher frequencies, they're going to go up a little bit more relative to the fundamental. So the amplitude of the higher harmonics go up even more. And you get a different slope to the envelope, right? So the fundamental frequency increases, the first harmonic increases, but the third harmonic increases even more, the fourth harmonic increases more than the lower ones, and the fifth harmonic increases even more. And this is referred to as, now how is this being controlled? How this acoustic waveform changes so that you get the spread of energy to the higher frequencies. Because what are you doing? You're closing your vocal folds faster, you keep them closed for longer. That changes the acoustic characteristics, so not only do you get higher amplitudes overall, you get a spread of energy into the higher frequencies, which helps you boost your vocal intensity. And that's how we control vocal intensity. It's all about, again, I will say to you, you have to visualize. If you keep your vocal folds closed for a longer period of time, visualize the video strokes we've been looking at. Keep them closed for a longer period of time. You close them faster, you open them faster. That changes the area between the vocal folds. It's all about what the glottis looks like. So you're really controlling glottal shape. And the timing makes a big difference in these acoustic characteristics. What time do you have? 4 minutes. 4 minutes. Okay, so we're going to finish this with, I'm pretty sure that was our last slide of that. These, like I said, these two explanations of how we control fundamental frequency, vocal intensity, very important. And now, the next time